So I hope what we talked about earlier today, at least my goal here was that to kind of, I realized that some of you have already started working on certain aspects of the land surface, and you probably face certain problems yourself already. I mean, my overall goal was to kind of raise questions. And that's why I, made you write these 3 questions. Obviously, why 3? I mean, could have been 4, could have been 2, but I did get like a bunch of very interesting questions. Some of them I cannot answer today because there are some very specific details about like particular methods, which are unique to the problem that you are doing. And so that is probably best answered by your supervisor, or I can clearly help you with that later if you get in touch with me, send me an email, or we can chat afterwards. But what I did is I kind of summarized some of the questions which I thought were relevant, and actually surprisingly there were many common questions, which tells us that at least I'm satisfied because I think I was able to kind of get you thinking in the right directions. One question that came up quite a few times was, I think you guys, like in the Arctic region, land atmosphere, several other groups also asked the same question. And we will see that land atmosphere interactions are extremely important in cold deserts. I mean, you would typically think that, hey, I mean, it's all covered with snow, maybe permafrost. And so it does not change. That's why it stays white year-long. High albedo, that's why it's very cold. Whatever solar energy is coming in, it's getting reflected out. However, why is that important for climate change? And we will see that in a moment later, that most of the strongest impacts, biogeophysical impacts of any kind of land use, land cover change, deforestation in the boreal forest, for example, the strongest impacts are observed in the Arctic. We will see why. Another important question that came up, which is, I got a few questions on carbon dioxide and land use and cover change. How do these measure up? I mean, should we pay more heed to land use and cover change or CO2? So we will see that question in the talk later. Feedbacks, many of you raised questions about feedbacks, and I will give you some examples, which you've probably seen. One important question that comes up often is urbanization. I have not incorporated urbanization in my talk. I have never worked on it myself, but it is certainly one of the major driving factors of land use and climate change, and probably more so in the future. However, if you think about it, urbanization, the footstep is very limited. In fact, if you look at most of the world, I mean, we look at India, and we see the major growth in the cities. Remember, these people are also coming from somewhere, right? So there is a movement from rural to urban areas. One thing that has happened is that now, since especially in the US and Europe, more and more agricultural land is going back to its original state because agricultural efficiency has increased. So if you look at Europe and North America, which is what maybe India and China will look like 20, 30 years from now, most of the things are happening in urban areas and they are very small. And so that's why the footprint of human activity, one might even argue that it's actually getting smaller. So that's a different problem. Earlier, our models are capable of looking at large things like large-scale deforestation, Amazonian deforestation, and we ignore cities. I think we need to have a paradigm shift and focus more on maybe very high-resolution models or nested models which look at urban areas, because more people are living there and these are very small. It's a good thing and a bad thing, obviously, because I will be able to show to you in one figure how agricultural land, when it's abundant, what happens to that. These are people are working on that. So urbanization is extremely important. We don't have global models that can deal with it. We need to maybe look at like coarse resolution model and then nest a high resolution model inside. But I think that most like US NSF, EU, both of these research programs are strongly devoting a large part of their resources towards urbanization. Now, we talked about also land use, land cover change. Now, land use and land cover are different things. Land cover is water, agricultural land, forest, or land use is what is the agriculture? Is it soybean? Is it bajra? Is it rice? Is it wheat? Or is it a palm plantation which looks exactly like a forest? So land use and land cover, they overlap, but they are very different. Land cover is easily measured by satellites, but land use not. Because if you look at a satellite image like the AI or something, a large, for example, you go to Southeast Asia, Malaysia. Large parts of Malaysia is very green because we have these palm oil plantations. But these plantations have come up over native tropical rainforests with very different characteristics. So they are more or less the same land cover, but very different land use. So we need to make that distinction first. Now, when we predict, like using the dynamic vegetation models, right? I mean, let me see if I can write on this board. I hope this is a marker to write one corner. I'm doing this because one time I was deriving the Reynolds equations in a tutorial and I wrote like a whole board of Navier-Stokes equations, whole board, and then I realized it's a permanent marker. So then I had to take the board and flip it over. So and the other side was a whiteboard too. Anyway, so basically we have dynamic vegetation models, right? So a DVM will go from like small grasses to like maybe small bushes and stuff like that to a large tree. So a DVM can do that. A dynamic vegetation model, because we know the laws of ecological succession. There are many people, one of my postdoc supervisors is very well known, and he has developed a model, the ecosystem demography model, which takes into account a lot of things like how far seeds disperse, how the seeds are competing, like a small tree and the grass are actually competing for resources. So who will win? Very complex processes. People take this into account to go from this to this. So these are kind of what we call like maybe land cover. I should not even be using this term. Let's call it a dynamic vegetation model or an ecosystem demography model. So,
sir, how many species like people know the ecological laws?
Actually, quite a lot. I mean, because ecologists have been studying these for like 200-300 years.
But if you see CNN, only like few.
Just because it's not in the CLM doesn't know that we don't have that information. So I mean, when we put it together in a dynamic vegetation model, we have our own limitations. But so there is a lot of improvement, scope for improvement in CLM, and if you look at say another model, Orchid, which has very nice, and my favorite model is the ecosystem demography model that has like incredible amount of detail. So there are several models, but those models with those kinds of details are very expensive, so that to couple with the climate model. So that's another problem. When you couple it with the climate model, you don't want the land surface component to be extremely expensive. So that's one challenge. So now what happens here is that when it goes from this to this, it's all happening because of climate and the soil, right? So these are interacting with the soil underneath. How much you have nutrients and you have climate and the sun and stuff like that. So climate, soil, they interact. So there is a natural process by which they grow, and we have a reasonable handle on, not as much as you like. That I will agree. So it's a good question that yes, we don't know a lot, but enough to get by. What we don't is, and that is the subject of a few questions here, is we don't know how humans are going to interfere with this in the future, right? When it's from like this tree to this shrub, maybe like 50 years from now we have a different climate policy or agricultural policy to grow cotton here. So we don't know that. That's why these DVMs can only, the models that we build can only talk about natural processes, not human processes. However, now having said that, I say this again, that there are models geared towards predicting human behavior as well. And some of these like policy-oriented models, people have not really coupled them in the climate modeling in that sense, the way atmospheric, land, hydrology, cryosphere models are coupled, human models have not been coupled. But people do those kinds of things. People do predict, like, for example, one of my friends, I work in Amazonia, and one of my friends has a very nice paper predicting future deforestation of Amazon. If you look at most of the future deforestation of Amazon things, it's like, let's cut down all the forest, or like 50%, or so kind of ad hoc. But what they did is they predicted how the roads are going to go, and since deforestation occurs only along roads, you can predict road behavior. It's not hard to do. I have made my own road model, that how road networks will expand. Roads typically follow topography, and so you can go and start with one small town and then you can build roads, which will be fairly realistic. So people are trying to do that. Can we do realistic models of human behavior? If we can do them, we can actually incorporate humans in this model. People don't want to do that because we change, right? I mean, so that's why I don't know if it's a good thing or not. That's why probably a better idea is to come up with scenarios that maybe we decide to become an agricultural society. What will happen? Maybe we decide to be an urban society. Maybe we want to be Gandhian and become a rural society. So build scenarios instead of predictive models. So now, having said that, I obviously I'm available to answer questions during lunchtime as well. But let me go back to the talk that I had originally scheduled to give. Is looking at land use, land cover change, and climate. One good question is like, do we need a separate land model for India? I mean, I say why, again, I could also say why not. Because the problem is that we don't have a climate model. All countries have their own climate models. Same physics, but calibrated. Like, I mean, India doesn't have a climate model, India doesn't even have a weather model, let alone a land model. So there are so many things that one would choose to do, or one could choose to take like an existing model and maybe we use the Met Office model and LMD model and things like that, tuned. So there is really no need as long as we can take a good model and make sure it's working for our conditions. So quick recap. We saw that the climate system needs land for efficient function, mainly through its role in the energy, water, and carbon cycles, and for soil moisture memory. Observations are limited. We are building land surface models and we are improving, but there is a lot that needs to be done. Okay. So now, when I talk about land use, land cover change on climate, let me start with, this is what I'm going to do. We'll talk about the effect of vegetation on climate and break it up into biogeophysical and biogeochemical. Observed influences, again, you can expect that there is very little observation, but look at some of the models and feedback. Both regional, most people only talk about global, but we talk about a little bit about regional and feedback. And I got like a bunch of questions on feedbacks and how these are incorporated in models. Another important question, land use, land cover change, and CO2. So we will address that as well. And the future land use, land cover change on climate. Again, many of these questions I'm surprised to see are in the list that you gave me. So that saves me some time. Okay. So there are two effects of land use land cover change. One is the biogeochemical, which is through carbon emissions. Okay, land cover is a net sink of carbon because it takes in carbon for photosynthesis. Through respiration, it releases most of it back out, but a small part is stored. Where is it stored? It's in the, say, the stems of large trees, in the roots of them. So that's where some of the carbon is stored. So that's why land cover is a net sink. When you change land cover, if you cut down trees, it cannot absorb any more carbon. That's why land use land cover change is considered a net source of carbon. So sometimes you will see carbon emissions from land use land cover change. It is not that the land is emitting carbon, it's that it's absorbing less carbon. So it's a, in that sense, it's a negative sink, and that's why it's a source. And that's where the biogeochemical effects come from. That if you deforest, then it cannot absorb as much carbon. That carbon stays in the atmosphere and creates climate change. However, also there are the biophysical effects through changes in albedo, roughness, and other things. Most importantly, like all studies suggest, is evapotranspiration. We don't understand it very well, but we see that it is a very, very strong impact. Other things we know quite well. So, let's do a very simple thought experiment in terms of biogeochemical impacts of land use land cover change. So, if I know that this projector is not doing a good job, so you cannot read the numbers. I'm going to repeat them for you. So, this is the land carbon sink. So, vegetation and soil stores about more than 2000 petagrams of carbon. Okay. Now let's say that I thought experiment, I get rid of all the vegetation and soil, and it's a desert land. So all that carbon will be released into the atmosphere, and let's just say that half of it is absorbed by the ocean and the other half stays in the atmosphere. What happens then is this is equivalent to an increase of 540 parts per million, more than doubling of atmospheric CO2, which leads to a radiative forcing of almost 5 watts per meter square and a temperature warming of 5 degrees. So that's what the land surface does with respect to CO2. Okay, it's a very important thing. Obviously, we don't expect this to happen. Something at that massive scale, but that's a kind of like the extreme impact that land cover can have. Now, let's compare that with the biogeophysical effects. Okay, so this is an experiment of total deforestation. Okay, so like all the forests in the world have been cut. This includes forests in Amazonia, Congo, Southeast Asia, as well as like the large boreal forests. Okay. If you add these up, it's a cooling of negative 1K. Okay? So, the biophysical effects, biogeophysical effects are only about 20% of the biogeochemical effects. They are very small. There are several reasons why this 1 degree happens. Okay? Could be changes in albedo, roughness, ET. Evapotranspiration, as you will see, is going to be more. Basically, again, what I'm saying is that if you deforest a large part of the world, everything will change. Albedo, the evapotranspiration, all these things will change, and also the carbon flux. These changes are the biogeophysical, and this is the biogeochemical. The carbon is biogeochemical and biophysical. The effect of carbon flux will be much larger, 5 times larger. But still, 1 degree is not a small number. Because moreover, the global effects will be small, but the regional effects are quite large. So first, let's look at the albedo effect. Albedo is nothing but reflectivity. How much energy hits the ground, how much of that is reflected. So a forest has low albedo, it's dark. Typically grasslands have high albedo because they are lighter. In fact, you were talking about like polar regions. Yeah.
So the last slide.
Yeah.
So the colors show the temperature.
Temperature?
The temperature difference.
Yes, delta T. Yeah.
So why do we see a pattern like only like South America and Africa and it's like
This is where most of the forests are. So this is total deforestation.
so that's why like if you deforest over that is like the temperature.
This experiment, it deforests the entire world, all the forests, but that's it, and replaces them with grasses and whatever the like all the succession vegetation is. But you do see also impacts elsewhere, right? I mean, the different teleconnections that we talk about. So most of the all the forests are here and Southeast Asia. These are the tropical rainforests, and these are the boreal and temperate forests.
Why warming actually over the tropics only on the soil?
Yes, let me come to that. So first thing that we see is that if we just look at the albedo effect, they were able to separate these things out. If we just look at the albedo effect, we see it's the forest grassland conversion, like very little change. Okay, so the forest over Amazonia, you cut them, plant grasses, albedo-wise little change. But the largest change is here because you can see the difference, right? Because all the grasses are white and the forests are dense, black. So that's why the largest changes are in the Arctic, because of the snow. So this is where land atmosphere interactions in the Arctic is starting. Even when you think it's snow, the problem is that small changes can have a large impact on albedo. Unlike in the tropics, where a small change will not have a large impact on albedo. So that's why there is a lot of effort on looking at the Arctic, purely from a biogeophysical point of view. We talked about the biogeochemical data in our context. Now, let's look at the roughness effects. Okay, so roughness is if the roughness is high, lots of big trees, urban or whatever, increases turbulent heat transport, which means more energy is transferred from the soil to the atmosphere more easily. That's why the roughness, higher the roughness, I got this wrong. Sorry, I got this. I think so. So basically, if you have a low roughness, it's going to create, because higher temperature in the soil, because less energy is being transferred into the atmosphere. No, this is fine. So that's the effect of roughness. Lower heat transport. So more of that stays in the soil, less of that goes out into the atmosphere for mixing. And if you have larger trees, buildings and stuff like that, more roughness, more heat transport. So we are going to see an effect something like this. Okay? And that is something, this warming is you see here, partly. Okay? That was your question, right? So the roughness contributes partly to the warming. The second thing in terms of biophysical that you will thought is the evapotranspiration. So when you have trees, they have deeper roots. So trees can have access to moisture. So when in trees, the evapotranspiration rate is higher, sensible heating is lower. In grasslands, with shallow roots, the latent heating is low, sensible heating is high. So there is this switch. Okay? And this is something that we know as the change in the Bowen ratio. So latent heat dominates, sensible heat dominates. And so if that's something that you are going to see in this kind of a situation again, this is going to be cool, warm and hot. And that's why that contributes the next part to the warming in the tropics. So basically the overall impact is the effect of these three things put together, and they interact non-linearly, of course. So another interesting study about, very simple study about, just biophysical effects, that you can see that it's significant changes in land significant increase in precipitation as well as increase in evapotranspiration. And the same thing in significant decrease in sensible heating and increase in latent heating. So if I manage to put this together and just compare the relative effects of albedo, roughness and ET. And this is done on a latitudinal basis. We see the blue is albedo. We see that higher latitudes there will be a strong albedo induced cooling because of the strong contrast between snow and forest. In the lower latitudes, that's where the challenge is, right? There is a small warning, but that's the problem. I mean, that is one area of research. Is still we don't have any. I mean, we are not convinced either way. Many of our, I guess it depends on the nature of the deforestation. Whether the forest will cut them, are you growing crops there, or are you growing just its desert? Another thing is that a lot of these land use models cannot make the distinction between land cover. So sometimes they will call it a crop, even though it's a crop of trees, for example. Let's say you have a timber plantation. You are in the timber industry, you grow trees which you supply to the paper mills, right? You are growing trees, a farmer is growing trees. If you have like a palm oil plantation in Malaysia, for example, you are actually growing trees, but these will be categorized as crops. So some of these, I think, the results are skewed by this categorization or mixing of land use and land cover. But again, the main thing here is that in the boreal regions, high latitudes, we know what is going to happen. Models are consistent. In other latitudes, probably a small warming, but I will show you the conflicting data here. Okay? But one thing is clear, like this is the total, the red line is the total change due to land cover, the yellow line is due to the biogeochemical effects, and the red line is, the blue line is the biogeophysical effects. So you can see that the biogeochemical effects are kind of contribute to most of the impacts. Biogeophysical effects are actually a small cooling, globally integrated, and this cooling is because it's reflecting this cooling is because of right here, albedo-induced cooling at the higher latitudes. So if you look at the global picture, that will tell you a total integrated like -1 degree cooling. Okay? But clearly, as you can see, that there is a lot more. For example, we talked about local and regional effects. Clearly, when we talk about land use land cover change, integrating over the globe is not the best idea. We need to look at specific regions because these regions respond differently. And there are reasons why. I mean, I don't want to get into this right now, maybe later. It depends on the background climate, whether it's energy limited or water limited, things like that. So there is a lot of research on this. But this remains an active area of research. That we know the Arctic region relatively well, but we know very little about the tropics and mid-latitudes and we see that the models do not give us the right signal, observations do not give us a signal that we can fully comprehend. Okay. So as we saw that like the biogeochemical processes dominate, and that's fine. But what is a physicist like myself, very little knowledge of chemistry, interested in? We are interested in the biogeophysical effects. And even though they are small, they are important because we don't really know which way they are going. That's why most of the effort in terms of biogeophysical research on land use and cover change is happening over the tropics and the mid-latitudes. Okay, integrated is smaller, but the most important thing to keep in mind that even though biogeophysics is small, regionally it can be quite large. So, any questions?
How the evapotranspiration and roughness are different?
What?
evapotranspiration and effect of evapotranspiration and roughness blend.
No, there is no difference. I mean, these are actually all connected. Roughness is a property of the land surface, which tells you the kind of its ability to generate turbulent transfer. So if you have a tree or like large buildings, large obstacles, mountains and things like that, they have roughness. The effects are similar or different depends on because they are coming from because of two reasons. So roughness influences the weather and the climate by changing the speed of the fluxes, so rate of transfer. The other aspect that you are talking about is, I will not just call it evapotranspiration, but the partitioning between, so let me go back here, like right here. So it's not an evapotranspiration effect per se, but this is, people call it a Bowen ratio. Okay? So basically the partition, the amount of energy that is coming in, how much of that energy will go out as latent and how much of it will go out as sensible. So that's the challenge. So this effect, it's not really concerned about the rate, it's more so about the way the heat is transferred. Is it as latent or as sensible? So compared to the, even though they have similar effects, down here, the problems are different. Roughness controls the rate of transfer, and the Bowen ratio effect controls the nature of energy transfer. Okay, so let's look at some observations. Again, I have already told you I don't have been able to establish that observations are limited. So don't expect too much. But all we can see are small signs of what is happening. It's very difficult to get by the complete picture. I'm not going to talk more about albedo and roughness because these are very well established. The challenge is with heating. Okay? We know that snow will reflect more energy than a tree. We know that. We know that a forest has more roughness and has higher turbulent transfer than a grassland which has low roughness. So we will not go there for the sake of time.
So can you please explain how sensibility or latency may differ when they come into the atmosphere? You just mentioned it's important to understand the concept.
That is a very important question. That's more for a boundary layer talk. So, but I'll do this quickly. So, I mean, that's actually, again, I mean, I'm glad that you are asking these mechanistic questions which are like this theme over here. Okay? So this is a, we know that when radiation comes in, let me start from the very beginning again. For everybody. So, net radiation coming in. And this is net radiation. This is incoming minus outgoing. Both short wave and long wave. Okay? So, that's the total energy that the atmosphere is getting. Okay? So, this is net radiation coming. So, now the earth heats up with that energy. So some of that energy is now transferred into the atmosphere as sensible heating. So that's just heat. And the process is very simple. So first, the lowest few molecules, like let's say if I have a fire, then put my hand in there, my hand is going to burn. First my skin is going to be burned, right? And that is because of a heat transfer mechanism called conduction. So that's just by conduction, the lowest few molecules. When they get warmed, then convection kicks in. Because warm air is lighter, it moves up. So, but that convection happens here. Okay? That transfers heat up and down. So right here we have conduction. And this is convection. So that's how sensible heat is transferred way up into the stratosphere also, like if there is a thunderstorm. Now some of the heat, because if there is moisture available, will be transferred as latent heat. How? Is that water molecules in the soil will cross the whatever, and then because the energy increases, the water molecules in the soil will evaporate. And as they evaporate, they carry this latent heat. So that's why these are two different things. Now, how does a sensible versus latent affect climate? First, as you can clearly see that if there is more sensible heating means that we can sense. So sensible heating contributes to a warming. Latent heating does not necessarily, because it's latent, it does not heat anything up. So there would be evaporation. Even though there is energy transfer, there may not be a warming. In fact, there would be a cooling because of further evaporation. So that's why we have fundamentally two different things. So when you look at a region where there is a more sensible, like here, like in this case, that there is less sensible, more evaporation, I can expect that this will be colder. Now, when I have more sensible, less evaporation, more latent, less sensible, this is going to be cold. More sensible, less latent, this is going to be warm. Okay, so that's how they differently affect the atmosphere. Again, keep this in mind that in terms of albedo, it's totally different, right? I mean, this will be looking at albedo effect, this will be colder, but that's why we are in this business, that things are not that straightforward. So now, the prevailing model of evapotranspiration, our understanding is that forests have more water, so they tend to evapotranspire more. They have deeper roots, so they have access to, they have a lot of leaf area. So if you look at the tree outside, it has so many layers of leaves. So it has more surface area to evapotranspire. But if you look down on the grasses, they have like one leaf. So it can only like transpire once, right? Because trees have leaves stacked one on top of the other. And that is why if you look at a car radiator, for example, it will have many layers so that it can exchange heat more efficiently. So it's just heat exchange. So this is the prevalent model. That over forests there will be more evaporation, over grasslands there will be less. Because of many things, the two major factors are the deeper roots and just more leaf area index. However, and this is something that we see, like unfortunately none of these lines are visible here. And I think the projector and we are probably not compatible. What I was trying, there's nothing visible here, right? I had some list of images again. What I was planning to show here, or what I can see here, is over forests you have less sensible and the pasture line would be here. Over pastures you have grasslands, you have more sensible, less latent. So exactly what we had expected. Now let me see this. So this is over Amazon, and this is a bunch of stations averaged in over western US and Canada. Here you see that the fact that the latent and sensible switches signs between forest and grasslands, you don't see it. Like here, evergreen forest, okay, and this is sensible, this is latent. So sensible is less, latent is high. In grasslands, like sensible and latent, more or less the same. In woody shrubs, sensible, low, latent, high. So this model of, this very self-explanatory model of low Cohen ratio, high Cohen ratio that we have in our head of our textbooks breaks down. In the tropics it works very well for us, but in the temperate regions it doesn't work that way. So again, that's why I'm saying is that we really need more data about evapotranspiration and soil moisture to be able to do a good job of understanding and modeling land use and cover change. So again, the key thing is we need to know more about evapotranspiration. It's still not clear to us that why that happens. Once it happens, we can try and find out what exactly happened, but a priori predicting them with absolute confidence, it's not possible. Now, it may be the case that that's just how it is, our model is wrong, and maybe the case that yes, in temperate regions, forests and grasslands, they have the same Cohen ratio. So it's possible that we need to go back and revise our understanding. But so far, the data and the understanding are not matching as well as we want them to be. So now, because of the lack of data, we rely on models, okay, to try to separate out some of these effects. And again, this is another, going back to the study that we saw, is like global deforestation, very similar to the study that I showed earlier. Now here what they did is, this is part of an experiment called LUCID, where they took like many different land cover models to see if there are similarities. Can we model the effects of land use, land cover change? And primarily they focused on deforestation. So you see that, you know, these are our model average. You see that deforestation increases surface albedo, as we expect. But there is a significant amount of difference between the models regarding this Bowen ratio effect. Some of them are saying that latent heating will go up, some of them are saying that sensible heating will go up. So is this a problem with the models or the data that we have to use to calibrate? Maybe so the question is that maybe the model equations are wrong. Maybe the model that we started off with, very simple, like, you know, Bowen ratio will reverse. Maybe that is wrong. Maybe we need to rethink that. Yes.
So the global one, how do we get the land use data? For example, I mean, is it complicated from one countries or?
Land use, again, is very complicated. But land cover satellites will give you anything. You can go today, like if you have your, you know, small portable modem, you can go and download it right now. By the end of lunch, you will have a land cover data. Very easy to do.
It's just based on satellite, not ground based.
Yes, it is satellites. Many of the satellites are calibrated using ground land cover data, and those are fairly good. The resolution is poor, but maybe you don't need that kind of like hourly land cover data. Who needs that? Monthly, weekly is definitely for AI and stuff. It's fine. So again, as I said, that is like this effect, the albedo effect we can handle, but the models cannot do the latent heating effect well. At least we don't know which one is right. There's so much difference, right? Again, this is very hard to read, but maybe the text will be visible. So that's why when we look at these models, and this used to be the temperature, this is ET, and this is precipitation. So the problem is that there is a lot of difference between the models in terms of evapotranspiration. The albedo effect we have been able to represent very well. Most models agree. But evapotranspiration and hence precipitation, there is a lot of uncertainty. In fact, all models have their own answers. And that's why if you take like one model and try to predict the impact of land use, land cover change in a global sense, you may not be getting the right picture. Okay? So now we talked about this global deforestation. People are saying that, you know, land use, land cover change is regional. And so we started looking at some regional land use, land cover change. And this is this is actually land use change. So it incorporates land cover from a very well-established data set. So this is the US in the 1700s, pre-industrial. This is early 20th century when the greens are forests, the reds are croplands, and the yellow and orange are mixed woodlands and grasslands. Okay? So you see that from 1700 to 1900, a lot of the forests are destroyed and you have crops there. But also a lot of grasslands and what we call the North American prairie, those are destroyed and now we have crops. So here the change is forest to crops, and over the Midwest and northern Great Plains the change is prairie to crops. And so what we see is the result that when you go from forest to farms, creates a valley, but when you go from prairie to farm, it's a coulee. So this is very important to keep in mind. So that's why if you just look at land cover, land use change, okay? That land use will not make a distinction between forest and prairie. It may say natural vegetation. When you say natural vegetation to agriculture, the results could be different. So that's why we need to integrate both the land use and the land cover to get the true picture. Another technique is because it's we did some work over where, so these are actually tree plantations. So this is the natural vegetation, current land cover, and these are tree plantations that were added in the model to see if, like, instead of crops, if we can grow trees for biological carbon sequestration. And we studied the impact of that, and we saw, like, actually a cooling effect and reduction in water availability. Another study that I'm going to talk about is, again, this is from some of the work that I have done, is looking at Amazonian deforestation. Okay, so the earlier global scale studies have looked at tropical deforestation. Matlab, like, let's see what happens if I cut down the entire Amazon. Okay, and we can see that that in itself generates so much uncertainty. In the boreal forest, we know what that is. In tropical regions, we don't know which way it's going to go. Now, the deforestation in Amazonia is actually not a clear cut, right? Let's see if this will work. Okay, so this is a 5 degree by 5 degree cell in Rondonian Western Amazonia. Okay, and so this is not a homogeneous clear cut. As you can see, the yellow regions are deforested. Actually, there is a road, okay, BR-364, which connects Brasilia is right here, and this is Rondônia, the capital. And so this is a road that connects going straight to Amazon. And if I zoom in, so this is what the road looks like. Okay, so they build a main highway, and then there are smaller roads coming out, and then there are secondary roads, tertiary roads, and these are actually what we call fishbone pattern, because that's what it looks like. They are. This is from Iconos, and the road. This is not the road. This is the deforestation along the road, and this is about like 2-3 kilometers, quite wide. Okay, pastures and farms along the road, and here is, like, an animation showing the growth of these two roads. They get connected by 2012, so it's pretty cool. Anyways, so if I look at zooming here, the forest area has high leaf area index. We expect the latent heat to be high and sensible to be low. And in the clearings, we expect the low leaf area index, low latent and high sensible heat. And again, this budget in these two cases are going to be different because the latent and sensible heatings are different as per our model. And what we were expecting is that when you have a clear air with warm, dry air, and you have cool, moist air over the forests. So warm air is lighter and cold air is heavier, so there is a horizontal pressure gradient. And in response, you will have what is called a vegetation breeze, which is very similar to sea breezes. And you will have like shallow cumulus clouds and precipitation only during the dry season, not during the wet season. So, if you look at, this is a ghost satellite image. If you look at the land cover and you look at the clouds, you can more or less see a pattern, and you can statistically analyze. And you will see that shallow cumulus clouds actually go up over the clearings, right? I mean, so basically, if you want to look at the popular notion of deforestation, it's followed by less precipitation and drought. That kind of breaks down right here in Amazonia, and that's why we need to look at these fine structures. I mean, I don't have time. So what I'm going to do is I'll show you one of the model simulations that we have done of let me see if I can get this to work. So yeah, so this is like vertical velocity at the medial height, and so this is the clock right here. Nothing happens in the morning, but I don't know, by this time, like late afternoon, you cannot see it well, but let's keep going, okay? So you'll see this vertical motions develop over the clearings, and you can see like strong updraft and shallow cumulus clouds. And then this was a nice day because of kind of like a front came in, and so these clouds organized into at the top of the front, and kind of they were not really destroyed, they were caught up in that. And it's very fascinating because you can see that this particular phenomenon, it's happening only because we have this kind of heterogeneity. Now, to give you an idea, as I said, that these are about like 3, 4, 5 kilometers wide. And if you think of a GCM grid cell which is 200 by 200 kilometers, so a GCM grid cell itself will be about this big, right? So clearly inside, I mean, there is no way we can represent these kinds of heterogeneity in terms of land cover. And so maybe the changes in evapotranspiration that we, or the mixed signal in ET that we are seeing from the GCMs is probably because it's not representing what exactly is going on inside. Because it's not representing like, you know, the vegetation breezes, and in fact it does not even represent like well-known factors like sea breezes, which dominates the weather. If you go to Chennai, for example, you get these sea breezes, right? You don't see that in a GCM. And so a GCM will consistently predict high, warm, humid temperatures, but the diurnal cycle, modulated by sea breezes, we are not going to see in a GCM. So that's why even though we have a good understanding, we may have a good understanding of land-atmosphere interactions. I saw a question about coastal regions, ocean-atmosphere interactions. Yes, we do. We know sea breezes happen, but we cannot represent them in a GCM. So that's one of the limitations. Now, another thing that I wanted to talk about is that, you know, the teleconnections. That so deforestation in Amazonia. You find that it has impacts on precipitation some other places. People are working on this, so it's not just purely localized, but the effects definitely regional and could be at a much larger scale. But now, as I said, that high resolution heterogeneous response forcings and responses cannot be resolved by the GCMs. So if you are looking at an impact of urbanization, which I guess many of you are interested in doing, I would say that you definitely need a regional scale model, like WRF, something that can do things at very high resolution. Don't go with VEGCM and other things. These are just climate models run at low resolutions, at 50 kilometers. Get something like WRF and run it at like 1 or 2 kilometers delta X. If you don't do that, you are going to miss out on the true picture of what might happen. You will get some signals, mainly the albedo signal. And maybe even, actually, you know, the albedo signal from urban areas might be even giving a cooling. Because think about it. What is the, if you look from a city, look at a city from top, what color does it have? What? Like white? Or dark, light or dark, that's my first light. Exactly. And so you're going to see the rooftop, which will have a high albedo. So if you run a global model with, looking at, a mega city. India has a mega city project now, so mega cities are being studied extensively. So if you look at a global model, you are going to get like an albedo induced cooling. You are not going to get any of these ET effects. The fact that in our urban area, where the rainfall that rainfall doesn't go into the soil moisture. That hits the pavement, goes into our drain, immediately gets into a river. So there is no moisture or evapotranspiration to begin with. Global model will not be able to catch. Urban breezes due to urban heat islands. Somebody asked me that as well. You are not going to be able to see that. So land use, land cover change. If you want to study that, you need to really go into very fine models. Unfortunately, fine models take up so much time, we cannot run them for 50, 100 kilometers. So again, that's a gap between resolution and coverage. So we need to be creative about like how do we bridge this gap. Because definitely I think what I have shown you here is that you need very high resolution to capture land use, land cover change and its impact. Because remember, this is something humans are doing at our own scale, right? And so it has to be small with an integrated effect. Now, another thing that I wanted to talk about is feedbacks. And you guys, how many of you are familiar with feedbacks? I see some, okay, but I don't see all. So let me just talk about feedbacks, and again I'm available for questions later. So often if you go online and you go to Google and say send me feedback, so you let them know how much you hate Google or whatever it is, how you like Explorer, something like that. So feedback is often thought of as a response, right? I mean, if I want your feedback, you tell me this lecture